Welcome to all. I am Assistant Professor Kuti Akshada from SND Engineering and Research Center, Evla. Today's topic is properties of graphene and applications. Graphene, a modern material with unique physical and electrical properties that could reshape our future. In this topic, we have seen introduction to graphene, physical properties, electrical properties, then other properties, how graphene is created, graphene's current uses, batteries, capacitors, transistors, graphene's future, and references. Introduction to graphene, the first two-dimensional material ever discovered, one atom thick of carbon atoms arranged in a hexagonal lattice, found in a graphite, coal, and created in other fashions. Hard to manufacture in large quantities. Just about all graphene produced is used for R&D within companies and universities. The strongest, lightest, and most conductive material known to man. Graphene has emerged as one of the most promising nanomaterial because of its unique combination of superb properties. It is not only one of the thinnest but also strongest material. It conducts heat better than all materials. These amazing properties and its multifunctionality makes graphene suitable for a wide spectrum of applications, ranging from electronics to optics, sensors, and biodevices. Physical properties of graphene. The strongest material ever measured, up to 150 stronger than the equivalent weight of steel as a rubber, and has the ability of stretch up to the 120% of its length, then recover its original shape. Extremely lightweight, it's said that a single sheet of graphene covering a whole football field would weigh less than 1 gram. Next, electrical properties of graphene. Graphene is classified as a zero overlap semi-metal, which means that either holes or electrons are charge carriers. Very high electrical conductivity when exposed to an electric field. In a vacuum, it had a mobility that was up to 250 that of Si outconducts copper by 1,000 times. Effective mass at the direct point is zero for both electrons and holes. One of the reasons nanotechnology research working towards molecular electronics are so excited about graphene its electronic properties. It is one of the best electrical conductors on earth. The unique atomic arrangement of carbon atoms in graphene allows its electrons to easily travel at extremely high velocity without the significant chance of scattering, saving precious energy typically lost in other conductors. Other properties. Only known substance that is completely impermeable to gas. Graphene oxide reportedly has the ability to attract radioactive material. Safer creation of quantum dots reduces the price from 1 million a kg to 100 a ton. Also has some optical properties that are being tested as we speak. Graphene has the ability to transmit up to 98% of light. How graphene is created. Mechanical exfoliation typically involves Scotch tape. Stick the tape to a graphite block. Use another piece of tape and stick the two sticky sides together. Repeat these processes 2 to 20 to 100 times. Press the pieces of tape with the graphene on a substrate. Mechanical properties of graphene. The impressive intrinsic mechanical properties of graphene, its stiffness, strength, and toughness, are one of the reasons that make graphene stand out both as an individual material and as a reinforcing agent in composites. They are caused by the stability of the sp2 bonds that form the hexagonal lattice and oppose a variety of inner plane deformation. Stiffness. The breaking They are caused by the stability of sp2 bonds that form the hexagonal lattice and oppose the variety of inner plane deformation. Next, stiffness. The breaking force obtained experimentally and from simulation is almost identical, and the experimental value of the second order elastic stiffness was equal to 380 nanometer inverse. This value corresponds to a Young's modulus of 1.1, assuming an effective thickness of 0.335 nanometer. Chemical exfoliation. The block graphite is submerged into a solvent and ultrasound is used to cause a splitting effect within the graphite structure. Prolonged exposure causes little platelets to be formed, enriched by a centrifuge. Next property is strength. Defect-free nanolayer graphene is considered to be the strongest material ever. Tested with the strength of 42 nanometer inverse, which equates to an intrinsic strength of 130 GPa. Next property is a toughness. Fracture toughness, which is a property very relevant to engineering applications, is one of the most important mechanical properties of graphene and was measured as a critical stress intensity factor of 4.0 plus minus 0.6 megapascals. Graphene oxides uses the same process as a chemical exfoliation, but graphene is oxidized. After the CE process, it is then deposited on substrate and reduced to parent graphene in some fashion. Chemical vapor deposition. The most common practice in creating graphene today. Typically, a copper substrate is exposed to a low pressure, 1000 degrees Celsius, annealing processes. Methane and hydrogen gas flows through the furnace. Carbon atoms from methane deposit on the copper, creating a continuous graphene steel. Silicon carbide. A small amount of silicon carbide is placed in a box with a hole in it. The box is sealed in a vacuum and argon gas and heated to 1500 degrees Celsius. Si molecules evaporate from the surface, leaving a layer of graphene. Optical electronics. Believe on mainly be used in touchscreens, OLED and LCDs. Graphene matches indium tin oxide performance in its basic state. Energy storage. Graphene is being experimented in both supercapacitors and batteries constructions. Graphene and transistors. Clock at 427 Hz. Create a false band gap by employing negative resistance. Another type of FET uses dual gate constructions. Applications of graphene. Graphene has been highly valued in the fields of chemistry, physics, materials, and energy due to its unique electrical, mechanical, thermal, optical properties and high specific surface area. It has both application prospects and the recognized as the revolutionary material. The field of energy storage. Graphene can be used to manufacture supercapacitors and super lithium batteries. The second in the field of optoelectronic devices. Graphene can be used to manufacture solar cells, transistors, computer chips, touchscreens, and electronic paper. The third is the field of materials. Graphene can be used as a new additive to make a new coating and anti-static material. The fourth is the field of biomedicine. Graphene has a good barrier properties and biocompatibility so that it can be used for drug delivery, biological diagnosis, fluorescence imaging, and biological monitoring. The fifth is the field of heat dissipation. Graphene heat dissipating films can be widely used in ultra thin and high power electronic products such as smartphone, iPad, and LCD TVs. Graphene lithium ion battery. The graphene material is only used in electrode of the lithium ion battery. In theory, graphene electrodes may have twice the specific capacity of graphite. In addition, if a mixture of graphene and carbon black is added, as a conductive additive to the lithium battery. The internal resistance of battery can be effectively reduces the battery rate, charging and discharging performance, and the cycle life can be improved. Graphene exists mainly in free forms in lithium batteries. Conductive additives, electrode composites, and directly as a negative electrode material. Graphene used as a fuel cell. A fuel cell is a power generation device that directly converts chemical energy existing in a fuel. The transport properties of graphene based membrane materials can be expected to solve the problem of presentation, penetration of the core component, proton conductive membrane, in fuel cells. Meanwhile, the nitrogen doped graphene catalyst can significantly reduce the cost of fuel cell. Graphene paper battery. Graphene oxide can be made to graphene paper. Graphene paper can function as a proton conductor, and the battery made up of graphene paper has a good initial capacity. The incorporation of graphene can increase the specific capacity and the utilization rate of active material of the battery by more than 10%. The negative electrode plate with graphene has a high porosity more than 70%. Graphene used as a semiconductor. Supercapacitors. Supercapacitors is an electrochemical energy storage device between transitional capacitors and secondary batteries. It has the advantages of high power density, fast charge and discharge, high life cycle, no pollution, etc. However, supercapacitors are currently restricted by electrode materials and the energy density is generally lower than 20 kg. Graphene itself has an ultra large specific surface area. Its energy storage density is close to that of lead acid batteries, which is an ideal electrode material for supercapacitors. Graphene is used in energy storage and solar cells. The performance of batteries and supercapacitors depends on the density at which they can store energy and the speed at which they can be charged and discharged. These functions critically depend on the nanostructure electrode that are used in these energy systems. Porous carbon nanomaterial are widely employed as electrode for supercapacitors and electrodes in commercial lithium graphene based nanomaterials have many promising applications in energy related areas. Graphene improves both energy capacity and charge rate is rechargeable batteries. The use of graphene can improve the photoelectric conversion efficiency and can be used as a receptor material in solar cells. Graphene can be combined with organic polymer material to form a large interface, which can increases the diffusion rate of excitons and carrier mobility in the battery and can be eliminate secondary aggregation due to destruction of the charge transport path. Graphene is useful for cells, supercapacitors, graphene batteries and catalysis for fuel cells. Graphene sheets has high strength and toughness in all sheets directions for diverse applications. As graphene based composites for vehicles, optoelectronics and neural implants. Defect free graphene might solve lithium metal batteries, dendrite problem, electrical short circuit and overheating of electrodes. These are the structures of solar cells. Storage of hydrogen energy by graphene. It is well known that the amount of hydrogen absorbed by material is proportional to its specific surface area. Graphene has the advantages of lightweight, high chemical stability and high specific surface area, making it the best candidate of hydrogen storage material. Then graphene is used in photovoltaic devices. Due to their excellent electron transport properties and extremely high carrier mobility, graphene and other direct band gap nanolayer materials such as transition metal, dichalogenides and black phosphorus show great potential to be used for low cost, flexible, and highly efficient photovoltaic devices. Sensor applications. Due to it is shown that the distinctive 2D structure of graphene oxide combined with its super permeability to water molecules leads to sensing device with an unpredicted speed. On the screen, these are the structure of photovoltaic cells. Graphene is used in photovoltaic cells. Then graphene composites. It is the first ever graphene infused carbon fiber helmet that capitalizes on the material's thin, strong and conductive, flexible and light characteristics to create a helmet that absorbs and dissipates impact better than your average helmet. It also disperses heat more efficiently, so it's cooler. Graphene is used as in sensors. Selective gas sensing with pristine graphene is also envisaged. On the screen, these are the sensors.